So this is the video for the assignment. Just because you are handing this for marks, I'm not going to give you all the answers, or I'm not going to write them out, at least just to make it slightly hard for you, I guess, realistically. This is a mark booster. I'm hopefully giving all of you full marks if you hand this in. So don't mess it up, I guess. Explain the differences between orbits and orbitals. Orbits are well-defined 2D paths around the nucleus that the electron takes. Orbitals are mathematical functions, so to speak, like 3D that describe the 3D probability density of the location of electron around a nucleus. Full electronic configuration and draw an energy level diagram. So you gotta go 1s2, 2s2, 2p6, 3s2. I'm looking for this general shape. Is it wrong technically to put the p block directly on top? No, but it's conventional to put it to the side and then the d blocks to the side of that. So if you can, do it that way. Silicon, after a 3s2, it has a 3p2 as well. So that's the last one for silicon. Hund's rule, that was the Hund's rule of maximum multiplicity. That stated basically that when filling up an orbital, all suborbitals were occupied with one electron each before pairing occurred. So each subshell had one electron before any pairing was occurring, and all those electrons had the same spin. So either it looks like this, or it looks like this for nitrogen, and nitrogen does not look like 1, 2, 3. This is wrong. That's what Hund's rule stated. You can give me an example. I just want to see some kind of understanding about what Hund's rule is. As long as you can explain it in words or give me an example, that's fine. Deuterium. Where's deuterium? Deuterium is a 4d1. So it's the noble gas here is krypton. Whoops. Krypton 5s2 4d1 for deuterium. Tellurium. Realistically, here we have a 5p4. So again, that's krypton 5s2 4d10, because these ones are n-1d orbital and -2f orbital, right? So where are we? 4d10 and then 5p4 is for deuterium. Oh, there's a blank page. I don't know why. Did I lose some questions? I think so. I don't know what that is, but I guess we're just moving on, because I feel like there should be some VSEPR theory somewhere in this assignment, but it is not there. So I don't know where that went. Interesting. So these are not possible because you can't have a 1p shell for L ranges from 1 to n-1, or 0 to n-1, which is in this case 0 to 0. So this is not possible. Here, for an L of V0, we cannot have an ML of -1, because ML ranges from negative L to 0 to positive L. For in this case, that's just 0. There's only one orientation for the s orbital to be in, with the ML of 0. So here we have 2p, so L equals 1, because the p orbital is a 1. 4s, and the ML has only one value for it to be 0. Here, iron is normally 4s2 3d6. We're taking away 3 electrons, so it loses all of those and just becomes, loses the 2 in the 4s and the 1 from the 3d and becomes 3d5. Selenium 2+ just receives noble gas configuration after accepting 2 electrons, so it becomes krypton. Zinc has a low melting point compared to other transition metals because of its 3d10 stable electronic configuration. It does not have any unpaired electrons to donate for metallic bonding to occur, so there's very weak metallic bonds and therefore a low melting point and boiling point. So hold up a second while I try and find the rest of this assignment. Alright, sorry about that. I found the rest of this assignment. There's 2 questions that were missing. So one of these is rank in terms of increasing melting boiling point. So this one is definitely going to be a question. So here we start with possibly the, we know the lowest boiling point are for the molecular compounds, and even then we have a range from nonpolar to polar to hydrogen bonding. So if we're ordering those, CH4 will be the lowest boiling point. CHCl3 will be the next because that's the polar one. HF has hydrogen bonding, so it will be higher boiling point. After molecular usually comes the metallic and ionic boiling points depending. So here we see 2 metallic compounds, NaCl, oh sorry, that's an ionic compound, zinc and vanadium. 2 ionic compounds, NaCl, AlCl3. Now again, how do I arrange these? Most probably zinc will be the lowest because that's the lowest of the metallic bonding series, so we'll put that there. All I want to see here is that you know to put that zinc is relatively lesser than vanadium. I want to see that zinc is lesser than vanadium because you understand the trend that vanadium has more unpaired electrons and therefore has a higher boiling point. Also that NaCl is lower than AlCl3 because this is a positive negative attraction, whereas this is a 3 plus minus attraction. There's more attraction there between aluminum and chlorine. They're also more similar in size, and therefore they will have a more stable lattice. I just want to see these true trends. The zinc should be relatively your lowest. If you put vanadium and if you switch these two, technically, I don't actually know if this is even correct. It's just the trend should be there. And then last you have carbon diamond, which is a covalent network solid, so it has the highest melting. I don't know if you could boil diamond. Highest melting point, relatively. Again, the boiling point is mostly for these things, which are gases. Right, so the boiling point, we don't really talk about methane as a solid. Okay. Lewis diagrams for SF4, so this would be 6 plus 28 is 34. So that's 8, and then each fluorine would have 6 around it, so that's 6 times 24. Sulfur has a lone pair, and therefore this is an AX4E, which is a seesaw shape structure, right? It will be polar. PF3, this is 5 plus 18. That's a weird number. 23, that's not right. Interesting. Oh, so that's not 18. Whoops, 21. 26, there we go. Phosphorus, here we have 6, and we know phosphorus has a lone pair. Therefore, this is an AX3E, being trigonal pyramidal polar. KrF2, well, this goes without saying that this is 8 plus 14 is 22. We have 4 plus 6 plus 6 is 16. So 3 lone pairs, AX2E3, which will be linear and also polar, I believe. Again, let me just check whether that is in fact polar. Is KrF2 polar? Oh, exceptions, KRF2. It is actually nonpolar because the lone pairs do end up canceling out. Again, we'll talk about this in class when we bring up the assignment. Where was I? So this is actually a nonpolar molecule because these three lone pairs kind of cancel each other out, just like three bonds in this shape would, and these two bonds cancel each other out. So again, the square planar and the linear do in fact yield nonpolar compounds. So again, exception, nonpolar, exclamation mark, exclamation mark. And yeah, we'll go over some of those questions in class, but I will see you in class. Alright, good luck. Peace.